Hello, everyone. I'm Liang Shunkan. I am glad to share our work here. The title of our presentation is Camera Calibration using a Collimator system. I will cover our work in 5 main parts: Introduction, Collimator system, Calibration method, experimental results, and conclusion. Camera calibration is crucial in photogrammetry and 3D vision. Even though many researchers have looked into this, we still face challenges. For example, poor lighting makes calibration tough, and calibrating in the field often requires large targets. Plus, long-range cameras need a lot of space for effective calibration. In this presentation, I want to present a new approach for camera calibration using a collimator system. Our method is simple, it only needs the camera to view a pattern from our collimator at 2 or more orientation. We've found that the movement between the calibration target and the camera follows a spherical motion model. This insight helps us reduce the number of parameters to be estimated. Finally, using this spherical motion model along with the planar homography constraint, we developed 2 solvers, a closed-form solver for multiple views and a minimal solver for 2 views. So, what is a collimator? It's an optical device that produces collimated rays. When light hits a point on the collimator's focal plane, it creates a beam of parallel light, making that point appear to be at an infinite distance. This means that cameras with different focal lengths can focus on that point. To help with calibration, we customize a specific star pattern on the focal plane as our target. We have several reasons to choose a collimator for our calibration target. 1. It creates a stable and controlled environment. 2. It offers extra geometric constraints, which improve accuracy. 3. It's compatible with cameras of various focal lengths. Next, let me explain our calibration method. We start by proving that the movement between the calibration target and the camera follows a spherical motion model. Based on the collimator's optical properties, we find that any 2 points on the collimator's reticle maintain a consistent angle when they are captured by 2 cameras. We call it angle invariance. Now, we fix the camera and calibrate the target as moving. From the angle invariance, we can get an equation. We prove that the calibration target can rotate around the camera freely, but there's no relative translation. This means the rotation can be any angle, but the position stays the same. From this angle invariance, we conclude that while the calibration target can rotate freely around the camera, it cannot move closer or farther away. The translation must be a zero vector. This pure rotation is what we call spherical motion. We also verified the spherical motion model through experimentation. A calibrated camera is used to capture several images of the target in the collimator. Then we applied the PNP solver to find the target's position and orientation relative to the camera. As shown in our results, the calibration target's positions are spread out on a spherical surface, with each pointing towards the camera's optical center. In the spherical motion model, the transformation matrix from the target to the camera is represented as follows. Here, TCP denotes the position of the camera in the calibrated target coordinate system, which is a fixed value. We looked at both spherical motion and planar homography constraints. By applying the orthogonal constraint of the rotation matrix, we established our final geometric constraints. There are a total of 8 parameters to be estimated, and each image will provide 5 independent constraints. Therefore, we need at least 2 images to figure out all these parameters completely. Given n images, we set up a linear equation system about W and A. W is the vector of intrinsic parameters and A is the vector of TCP. There are 11 unknowns. When n is greater than 2, W and A can be solved linearly. When using just 2 calibration images, we applied a hidden variable technique for resolution. Finally, bundle adjustment jointly refines the camera intrinsic and motion parameters. It is worth noting that the spherical motion constraint reduces the original 6n motion parameters to 3n plus 3. We tested our method with both synthetic data and real images. The results from the synthetic data showed that our algorithm outperforms others. We also tested how well our initial value estimation and sensitivity analysis work for imperfect spherical motion. Our results show that our method performs better than others, even with a noise level of 15 mm. Real image experiments also support our findings. The collimator demonstrated better accuracy when compared to results from printed calibration patterns. The struction from motion result outcomes indicate improved accuracy in the collimator image and highlight the beneficial impact of the spherical constraint on accuracy. In conclusion, we propose a calibration method using a collimator system. The collimator provides additional spherical motion constraints for camera calibration. Experiments show the collimator images provide better accuracy. You can find the demo code on GitHub. Thank you for your attention.